Okay, yeah, so I'm Jonathan Mugan. Let's see, I work for a small AI company here in Austin, Texas. We do a lot of AI work for the Department of Defense. Today, I'm going to be talking about an open source reinforcement learning project called RLlib. And so the So reinforcement learning is an effective method for solving problems that require agents to learn the best way to act in complex environments. And so RLlib is a powerful tool for doing reinforcement learning where you have multiple agents that have to work together and you have hierarchical agents. So when I first started learning about RLlib about a year ago, there are a lot of resources for learning how to use it, but those resources are very academic focused, it seemed to me, and they didn't really tell you how to apply it to your problem. They were more along the lines of, okay, well, import Atari and then do Atari.run, and then you get a bunch of graphs, and you're like, okay, that's great, but how do I apply it to my problem? And so I had to struggle quite a bit to learn how to apply it to my problem. So I'm hoping to give you a talk today to minimize your pain. And so my understanding is I'm supposed to talk for about 25 minutes. So that would be like 7:35. I stop for questions. So I will do that. And then today is just a kind of a quick overview. As you can imagine, in 25 minutes, I'm giving a longer talk at Day to Day Texas on June 13th here in Austin in person. So that'll be a 90-minute talk where we'll be able to go in depth. But for today, I think this tutorial should give you enough of the major concepts to kind of whet your appetite. And if you wanted to start diving in, you could get started. So the first thing is, reinforcement learning or problem solving, of course, is a big area. And so you want to make sure that RLlib is the right library for you. So I made this little handy chart here. And so, the first thing is your problem really a reinforcement problem where there's sequences of actions, like a robot going from one place to another, or a bunch of actions where the action you take in this situation in part depends on the actions you took or your agent took in previous situations. So, so if your solution requires like maybe one decision, maybe you make that decision many times, so maybe it's like A/B testing or something, then you want to go to the left. But if your decision requires multiple decisions in a row, then you'll go to the right. And then, so if it's kind of a low dimensional decision, which ad do I show or something, you could do like A/B testing with Facebook reagent. So now's a good time to say there's a lot of links on the slides because I want to be able to get you going so you can look for more. And so these slides are also with the code at the GitHub repository at Dayumbra, Texas, practical RLlib tutorial. And I put it in the chat at the beginning, but I'm told that I should put it in the chat again because you can't have access to the chat for the time before you join. So we'll add that again later. But so you don't have to write down all these links or anything. You should be able to find that online as well as the code. So if you're low dimensional, you can do A/B testing. If you're kind of higher dimensional for a single problem, you can do Bayesian optimization with Axe and Blowtorch. So you can look at those two things. Now, if you're more on if you think, okay, yeah, I'm doing reinforcement learning, so then your decision is, okay, am I doing kind of standard single agent reinforcement learning, in which case you want to go to something like Stable Baselines 3. And there is so a lot of good links for that. I used that for a while, and I used it until I needed to do offline reinforcement learning or multi-agent reinforcement learning. It's less designed for those things. But Hugging Face, which is a big name in natural language processing and has some great stuff, has just kind of gotten into that act with decision transformers. So Stable Baselines 3 with decision transformers might be a good place to start if you're doing single agent stuff. So look at that there. However, if you're doing multi-agent, swarms of agents, offline or online, offline means that you have just a set of behavior that agents did and you need to learn from it. You're not actually in the world. And online means you're in the world and your agent can explore in real time. But especially for multi-agent stuff, then you'll want to use RLlib, and that's what this tutorial is. So, of course, reinforcement learning has been around for a long time. It started with animal reinforcement learning with Thorndike, 1898, and then became behaviorism with Skinner and the famous Skinner box, and it was formulated into artificial intelligence in about 20 years ago with Sutton and Bartow. At least in their book, kind of brought it into the consciousness of the ML researchers. So, of course, there are papers before that, going back decades, of course. But that book was kind of a catalyst in the mid to late 90s. And so, in a nutshell, reinforcement learning, you wander around till you get to where you're going, and then, oh, I found the pot of gold, and now I kind of want to remember how I got there. So you have this value function that says, okay, the pot of gold is great. Being near the pot of gold is pretty good. And then being near the pot of gold, well, that's pretty good too. And then you can kind of go all the way back to the beginning, kind of like a bucket brigade algorithm. And so eventually, if you wander around the world enough, you will have a policy of what to do in any state. And now this is kind of where reinforcement learning was until deep learning took over. And the difficulty with this kind of reinforcement learning, they had stuff like tile coding and stuff, but the difficulty with this kind of reinforcement learning is as the state space explodes, you can't explore the whole thing. There's just too many permutations of all the variables. And so deep learning was able to take that beautiful generalization of deep learning and be able to say, okay, we've got a neural network that represents your state. And so now we've got, we can use the neural network to represent your state and your policy and all that stuff. And so you don't now have to physically visit every possible state because the system can generalize. And this is what has helped reinforcement learning really move along. And so RLlib is built on something called OpenAI Gym. And OpenAI Gym is under the assumption that you're using a deep neural network. So when you use RLlib, you get neural networks for free. You don't have to build your own neural network. You just kind of say what you want it to look like, and it builds it for you. And so this tutorial is going to focus on RLlib. Now, if you, here's a couple good links to the new Sutton and Bartow book, and Lulian Wang, if I'm pronouncing that correctly, has a beautiful blog post to explain, and that's always a great place to start if you want to know about reinforcement learning in particular. So here we are in RLlib. And so what RLlib started off is built on Ray. And the point of Ray is to enable distributed computation. And distributed computation is particularly hard for reinforcement learning because you have to keep all of your policies running on the different machines in sync. So you need some sort of architecture that keeps everything in sync. So as you're learning over here in this machine, and everything you learn on this machine needs to be transferred over to this other machine where you have this other guy or gal or robot learning, and then over on all those machines. So you need some kind of mechanism to keep it all straight. And that's what RLlib does. And so you have this like one worker here with a copy of the policy and a reward function, and it interacts with an environment. And of course, then you can scale that out as many workers as you want across multiple machines. And what happens is it gets a bunch of samples of state, action, reward, get brought into a central place where the policy is updated. And then those get broadcast back out to the workers. And so that is the kind of the reason of RLlib to exist. However, that's not my favorite part of RLlib. My favorite part of RLlib is the abstractions for hierarchical and multi-agent reinforcement learning. And so that's what we're going to focus on. So I told you at the beginning that what we want to do is enable you to use RLlib for your problem. And so that means that you need to know how to set up your problem within the framework of RLlib. So what we've done here is we've created a really dumb custom environment. And it's the dumbest possible environment we could imagine that still has the criteria we care about, which is multi-agent and hierarchical agent. So you have these robots in a chicken field. And the scenario is you have two robots in the chicken yard, and the robots want to capture the chickens that are most like them. So the robots and the chickens have their personality measured with the ocean model. And so they get a reward for getting to the chicken fast and for getting to a chicken that is most like them. So if the robot is particularly neurotic, it's looking for a neurotic chicken. And so there are two robots, so you kind of have a multi-agent aspect to it. And each robot has two different policies. First, it has to pick the best chicken, and then it has to make its way to the chicken. So both of these things are very simple, of course, but we want to start with something the very basic so we can see the fundamental pieces and how they fit together, because the abstractions of RLlib are a little complicated. And so I mentioned that RLlib is built on top of OpenAI Gym. And that OpenAI Gym allows you to automatically or to easily use deep neural networks. And so the way it does that is OpenAI Gym has this thing called a state space, and we'll see that. So what we have for our current state space that we need to move into that deep learning state space is we have a set of chickens. Each chicken has the ocean model, so it's a vector of 5. The ocean model is 5 personality traits. Each chicken also has a position, X, Y, and each robot also has an ocean vector. And so that's the high level. And then at the low level, you've got the robots and the chickens at the positions. And then your high level action space is which chicken to choose. And your low level action space is just move north, south, east, and west. And the episode ends when each robot gets within a distance threshold of a chicken. So here again is the link to the code. And so here is the concept diagram of the abstraction space. So this is what we're going to go over in the next 10 minutes or so. So the first thing is this AI spaces. And I was just talking a moment ago about how you can easily take that space I just talked about and moved it into a machine learning space. So if you see here, you do from gym import spaces, and you have robot position space equals spaces.box. And so box in AI Gym is a way of just, you define a bunch of variables and it creates a vector that throws them all together. And so you say, okay, what's the dimension? Okay, it's shape 2 for X and Y, and then the low and the high. And then for the ocean space, which is the next one, is also a box. You have the 5 num ocean features, and this is a float between low and high. So that's pretty straightforward. But then you can do your high level observation space. You can do spaces.dict, which is you can do chicken oceans, which is your chicken ocean space. Then you can do chicken position, your chicken position space, your robot ocean space. And so you have all these little spaces that are built up on top of each other. And normally when you're doing deep learning, you have to do this kind of tedious thing where you flatten them all out into a long vector. But by using the OpenAI spaces, it takes care of that for you. So that's a real nice thing. And so you can actually have this dictionary thing. And then one little gotcha is you see that spaces.dict. And so dict, since OpenAI Gym came out, became type hints for Python. So don't confuse type hints dict with OpenAI spaces dict, or you will have an angry weekend. Okay, so that is the spaces. And then the other big abstraction that OpenAI created besides spaces was this thing called an environment. So the environment is how you interface between your reinforcement learning, machine learning code and your actual environment you're training on. So in our case, it'll be the chicken yard. And so the environment is a class that has four important methods: the reset, the step, the render, and the close. So reset is just start a new episode. Render is if you want to have a picture, like a video of going on what's happening, and then close is when you're done. And then, but step is the important one. So at every time step, your OpenAI gym environment goes through three parts. It takes, here we are down here, I hope you can see it, it's a little small. It takes an action dictionary that is filled by RLlib for your actions that your agents are going to choose. And that's because RLlib is holding on to your policy. So if you remember way back, RLlib takes the policy and copies it around. So RLlib chooses the action. You get your action from RLlib, and then you call your state, your local state. So in our case, we'll call it a chicken yard. And then you pass the relevant information after calling your chicken yard back to RLlib. And in this case, the relevant information is the observation of the chicken yard, where the observation is defined in terms of those gym spaces that we saw before, the reward you got for whatever action you took, or whatever state you reached, and whether or not your agent is done, or any other information you want to pass. So I just said your agent is done, but then RLlib actually does multi-agent. So what RLlib has done is they have abstracted or subclassed from the RLlib, from the OpenAI environment into this multi-agent environment. So I'm gonna go back. So this is the OpenAI gym environment. RLlib has a multi-agent environment, and RLlib subclasses that or extends it. And then you have this thing called an RLlib agent. And so you can have many agents because you're multi-agent, and you can even have agents within agents because we're hierarchical. So you have on this side, your physical agents, and then for each physical agent, you can have multiple virtual agents, and then you can map virtual agents to policies. So if you have multiple agents, like a swarm of robot chickens running around, and you want them to all learn together, they can all share a policy. And so the way that's done in our case here is we have two robots. So we have two physical agents. And then there are actually four virtual agents. Each robot has a high-level agent that chooses its chicken that it's going to go after. And then each robot also has a low-level agent that is navigating to the chicken. So, and those two, even though we have two robots, we still just have one high-level policy. So one robot can learn from the experience of another robot. And the way this is done in RLlib is you just pass, when you pass back your observation reward information, you just use your agent ID that acted in this instance. If your agent didn't act because it's a high-level agent and you've already chosen the chicken, you're just waiting to get there, then you don't pass back the high-level agent. You just pass it. These are dictionaries, and that's really the beautiful aspect of it. So now I know this is a ton of information in 25 minutes or so, but hopefully it'll be enough to get you going with these major abstractions. So here you are, you have your target system, and then your environment. So the first thing you want to do in reinforcement learning is to make sure your environment works. So let me just show you how that works here. So we've got if we go up to demo, so we've got in demo, there's three things. There's your RLlib environment, which I believe is the thing here. And then you can train, and then you can look at the policies. We're not going to have time to train or look at the policies, but at the day-to-day Texas, we will. And because that's an hour and a half. So you've got your things look differently suddenly all of a sudden, but hopefully this thing will pop up. Where'd it go? Okay, there we are. So here are robots running around. So they're just randomly walking around till they find a chicken. And so here I am printing out the reward. And so at this point, we're not even using RLlib. We're just testing the environment, and that seems to work okay. So we'll stop that. And then go back to our code here in the last few minutes we have. And so you test the environment, and then, so you have this trainer that can then run the training in the actual environment that calls the MultiAgent agent, and then the trainer can define an execution plan. So you can use the basic ones in RLlib, or you can define your own. These are actually somewhat complicated, but you usually don't have to do that. And then for each agent, you have a policy. And so what we have over here is we're assigning a policy to the agent ID. So if hi is in the agent ID, then we have the high level policy. So we just assign these policies to agents. And then you can run the trainer. And so you can do, there's training, there's a couple ways you can train. You can use array tune, which is initially made for hyperparameter tuning, which is actually the most common, or you can just call it individually. And then of course you can define your own custom policy and model, but if you don't do that, it'll just use the default, and it can use either TensorFlow or PyTorch. And so basically, given the spaces that you defined, it automatically, and whether or not you want TensorFlow or PyTorch, it may do some other stuff like JAX and stuff, but I just use TensorFlow and PyTorch. Depending on how you define your spaces, it automatically builds the neural network to match those spaces. And there is a huge configuration that you can set up. So everything is customizable. And so this is where you actually run it in this your RLlib train. And here's where you can do tune.registry and add your trainer and train, or you can do your trainer. And so when you run this, it automatically hooks up to Tensorboard, and you see 57 graphs of all the stuff that's happening, your reward of each agent, you know, the episode length. So you see here the episode length goes down as it gets faster, it's getting to the chicken. And so all the information you would need to track this is automatically done in Tensorboard. And so if we look at the training results, if we let it run on our laptop for like an hour or something, you can see that it gets marginally better at finding the chicken that's most like it. And it's really good at, once it's picked out the chicken, of getting to the chicken fast. And you can add whatever restrictions you want in there, like they can't choose the same chicken or whatever, however you want to do that. That would just be in the reward function. And then here's training results. The time goes down, of course, as it gets faster. It doesn't have to wander around, because what we saw is it wandered around with no knowledge at all. It's just choosing random actions. So if you run it after it's trained, then the robots go right to a chicken. So so you can then, of course, once you've trained your policies, you can load them up and then use them. You just pass in your observation space, just like you did for the neural network, and then it'll pass you back an action. And you can actually look at the policy. So if you do demo look at policies, you can look at the actual weights if you want, or you can look at the sizes. So all this, every time I just show a screen that just must flash by your eyes, there is a hyperlink underneath saying what file this screen is from, so you can go back and figure out everything you need to know. And so now we have seen all these abstractions in a whirlwind. And here's some additional resources in the last minute. So there's the paper, the GitHub, the documentation, and there's discussion. They have a discussion board. So if you have questions, someone will usually respond in a day or so. There's also a brilliant video of offline learning. So if all you have is all you has is the actions of the agent, you're not actually control the agent in real time, you can check out this video. And so reinforcement learning is a gradual stamping in of behavior. And now we use deep neural networks. But of course, deep neural networks require a lot of training, even in simulation. And so what we do at the Umbra is we focus on building good representations. Now, of course, today we didn't build any good representations. We just were trying to figure out how this thing works. But that's what we do at the Umbra. And then this was, of course, a whirlwind. And you can go to Day-to-Day Texas, and if you use the code Mugan, you get 20% off. Lynn, who runs Day-to-Day, just sent me that today. So that's kind of fun. And that's my talk. Thanks for listening. I can take any questions for as long as the moderators will allow.
Oh yeah, go ahead. If you have questions. I'll start with a question if nobody has a question. So you said there's like these agents, they are sharing information with each other, but aren't they like have like different goals? You know, my question is like, what kind of information they're sharing with each other? Like, if that's a question, I'm not sure if the question makes sense, but I know you said like they're agents, and then they all, like this agent has a goal to chase after a chicken that is more like itself. Right, so but then that means the agents are a little bit different, right? So my question is like, what they're actually sharing with each other.
Yeah, so in the step function, let's see, I'm going back to the step function. I'll get there eventually. So in the step function of the OpenAI Gym environment, or the RLlib multi-agent environment, you get an action dictionary, which is a mapping of your agent ID, which is a string, to whatever action is chosen. So that action dictionary comes from the policies of the agent. So in order for those actions to be chosen, that depends on what you pass in the return value of this step function. So the return value of this step function returns an observation, a reward, where those are also dictionaries keyed on by the agent ID. So if you want the agent to have any knowledge of any other agents, then you put it in that observation of the agent. So you can set it up however you want. And that all takes place in this step function, all the meat. So what RLlib helps you do is it helps you share the policy, if that's what you want to do. So when it does this learning step, so here we have agents mapped to policy. So in our case, we've got only 2 actual policies, and we've got a low-level policy and a high-level policy. So that means that level of sharing, so the level of sharing I just described with the observations reward, is up to you. You have to code that yourself, however much sharing you want to happen.
Okay.
But then once you map the agents to policies, I'll get there. Here it is. This update policy then gets pushed out. This gets pushed out based on how you mapped your agents to policy. So if you mapped all of your chickens to the same policy, every chicken's going to learn from every other chicken. So if you had like a role, let's say you wanted aggressive chickens and curious chickens. Maybe you wanted 3 kinds of chickens. You had aggressive chickens, curious chickens, and frightened chickens. Then you might have 3 different policies. And so 1/3 of the chickens would be matched to the aggressive policy, and they would learn from other aggressive chickens. You can set it up however you want. And so that's how the policy mapping works. And then in terms of the reward and the observation, that's all completely up to you in the step function.
Right. Have you seen any like real life like robotics applications for this, or is it still like very early? Like anything, like I'm more interested like legged robots, and I wonder if this can be used like as it is maybe in some real world applications when you make a robot that learns how to walk, for example. I know, like, if you use a real robot, probably going to destroy it before he learns anything, but maybe you have to simulate it.
Yeah. So yeah, one of the most exciting things in reinforcement right now, in my opinion, is how good simulation has become. And so there are a lot of companies increasingly training in simulation and then translating directly onto physical robots.
Yeah.
And there's a lot of stuff with Isaac Sim from the NVIDIA. Google's working on that. Some people at Facebook had a great paper about a year ago about leg robots and simulation, and then they had to learn to translate it to the real world, and then the leg robot could run in the real world. Yeah, in fact, yeah, so learning to navigate and walk it is one of the big things. And then you might want to, it might be that, hey, maybe you want to learn the robot individual skills on its own, and then later on have them come train together. Or, you know, maybe you want to try to factor that out a little bit. That might be up to you. Although I saw a paper, and I don't remember who it was, about 6 months ago, where they trained these soccer players in a simulated environment. It looked like a video game, but the soccer players like had bones. Like if you didn't give them any forces, they would just crumple like a dancer or something. And so they first did motion capture on real soccer players so the things could kind of stand up. And so at the early games, they look like when my kids were like toddlers playing soccer, just kind of running around and falling over. But then, you know, within a week of training, it was amazing. They could pass the ball and shoot. And it's really coming a long way.
Yeah, I saw something. Yeah, it was a paper from Google also, but they went the other way where you're not using. You're actually using the real robot in real world, using some reinforcement learning algorithm. But they had to do all these tricks where when they detected some sudden move, they practically limited that from some regular software code. So like when you take when the leg would go like all the way like crazy, they will actually detect that. So that's too big of a move, and then limit that. And that's how they were able to practically keep the robot intact or somewhat intact and still learn from the real world. But they actually used like a real robot in the real world with some reinforcement learning algorithm. But they had to do all these, as I say, like they had to do all these little tricks where by the end of the day the robot wouldn't get messed up, because there was like a lot of times like the robot would make all these like there were like shakings and sudden moves, and it depends on what you learned, but to that point. So that was kind of interesting, a paper that I read where they didn't use a simulation, but I think it's probably better to start in simulation.
Yeah, no, and then yeah, one of these, I think it was some people at Berkeley had a paper where they had a second neural network that once the thing was in the real world, learned to translate the real world input into input that looked more like a simulation. So that the neural network trained in simulation knew what to do with it.
Yeah.
So, and that was really cool. And the physics of the world is being increasingly well represented. So like I saw a video last night, and I want to say it's people from Google, where they had robots screwing in nuts and bolts. Like you had a nut and a bolt. Like imagine all of the contacts that has to happen and the frictions and all that stuff. And
it was like a robot hand.
Yeah, but not like one of our hands, more of a pincher. But the fascinating part was the screw and the nut and the bolt. They could actually simulate the nut on the bolt, and you know, with the corkscrew thing and
all that.
Yeah, and then of course, then they could, once they were able to do that, they were able to teach a robot to do it, and then. Actually, they didn't teach a single robot. They had like 1,000 robots all lined up in some kind of dystopian factory. They're all screwing in bolts, and yeah, that was pretty cool.
That's neat. Yeah, anybody else? Questions? Sorry, I kind of monopolized. I'm excited about robots.
I have a couple of questions. Let's start with a simple one. The reinforcement part. What is it? Reinforcement learning, as far as I recall, is when you don't give it a yes, no answer. You just tell, oh, you're getting closer, oh, you're getting closer, stuff like that. You get the neural network. It's like riding a bike and trying not to fall. So it doesn't tell you you fell or don't fall. It tells you, oh, you kind of maintaining the balance. Just take a little bit to the right, a little bit to the left. This is reinforcement learning, the way I remember it. How does it represent in your little demo? What's the reinforcement part? What's the difference from other type of learning?
Yeah, so as your, let's see here. Now we want to go the other way. So when your robot gets next to a chicken, where is the reward function? There it is. So it's punished on each time step. So it hates life and it gets punished on each time step. So it wants the episode to end as soon as possible. And so it gets a small negative reward at every time step. And then it gets a reward when it reaches the chicken. And it gets a reward proportional to, I just take the dot product of its personality with the chicken's personality. And so as it's wandering around, it isn't given which direction it should go. It just says, you're in pain, 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 you're in pain. Oh, the pain ends, you get a small reward. And so it learns then that, and there's a lot of different reinforcement learning algorithms and they all work slightly differently, but it still is the same principle of, well, being out here in pain is bad, but being close to the chicken you're going to is good. So do that. And so then it kind of learns a gradient of where to move. It's like, okay, out here away from the chickens is painful. But as I get towards the chicken I've chosen, the gradient says I just should keep going.
Okay. So it's kind of an optimization problem.
Exactly, yes. Mm-hmm.
My second question is, you showed us the robots before you start training when the chickens are like stop on their way. And you said you let learn for an hour. Did they become much, much better afterwards? After they trained?
They do. Let's see if I have this demo, how much bit rot it's had. Let's see if it'll run. But yeah, they run more or less right to the chicken. Let's see here. Now, it's probably bit rot, but we'll see if something comes up here. I didn't actually think we'd get this far in this 25-minute talk, so I didn't prepare this.
It's okay.
Well, the computer has a thing. It hasn't crashed yet. So that's, yeah, so here we go. Ah, there we go, a little faster. This guy's pretty dumb. Come on, man. Is this really accurate? This doesn't seem right. You can't do that, bad.
Got stuck in the corner.
Yeah. Maybe, I guess he didn't learn over here so well. I tried a few different things. It usually learns, but reinforcement learning is kind of finicky. They will, let's see, let me make sure I'm running demo after training, but I may not be actually running the checkpoint. That's any good. But yeah, so they always start in a random place. So yeah, the learning, reinforcement learning, there was a paper that came out a couple of years ago called Deep Reinforcement Learning, or it's actually a blog post, still doesn't work. And they showed all of these examples where, yeah, when it works, it's kind of, oh, okay, that guy found it right away. And this guy's still having trouble. This one robot's just dumb. He stands in the corner. So, so you have to muck with it a little bit. And I don't remember, it may not even be running a real policy here, but it generally learns how to do it. This simple thing, you would of course learn, you would hope that it would learn something as simple as this. In fact, we saw it on the chart of the thing going down, of the reward going up and the episode length going down. Here they are. And one guy found it fast, and this one robot is just dumb. Now they're using the same policy, so it's not that one robot's dumb. It's like they get to the corner and
Maybe
they
it's a
can't
different-
figure out what to do.
Maybe he has a different characteristic. Maybe he's too neurotic and can't find a neurotic chicken.
It could be because they do start off with different personalities. And so it could be that this one had a personality that matched the chicken and then, oh, now he's gone. Like he figured out how to leave the game. So I think that
He doesn't like chickens.
yeah, well, I think he attained consciousness, I think is what happened.
Now that's why now he got really smart.
He's like, I'm not doing this stupid chicken game.
Yeah, I think Chris has a question. Chris, you can unmute.
Yeah. With on slide 25, you have a diagram that's showing just sort of this flow between the actions and the policies, and there's like there's robot one high and robot one low, like, and both of those appear to be feeding into a high level policy. Is the high and like, is that, am I just not understanding with like the way in which that stuff is labeled and how that relates to the high level policy, or how does that work out?
Yeah, so that's because I'm an idiot. It's supposed to be like this. So the two high level robots use the high level policy, and the low level robot. Yes, thank you. Wow. And then the low level robots use the low level policy. Thank you. Yes. Hopefully that makes more sense. Oh wait, dang, I still
One
wrong.
more.
I can't. There we go. Low to low. There we go. Yeah, that's how it's supposed to look. Sorry about that. My heart was in the right place. It's just I'm not good at writing stuff.
So if I could jump in here, there have been a couple of questions in the Zoom chat around like what is a reward exactly, and why is it that it's so useful for these robots and the reinforcement learning policies?
Yeah, so you would actually rather not use reward if you didn't have to. So kind of tying into the first question. So if you use just intelligence, you would say, oh, okay, here's the difference in vector between this robot and the chicken, and you should just write a control law for the robot to go to the chicken, right? That would be the ideal thing. And so you shouldn't use machine learning if you don't have to. If you know how to write a control law for what you want, just write a control law. The second best thing is if you can't write a control law, my cat is tearing up the chair over there. Hey, cat, bad cat. Got it. If you can't write a control law, but you know what the robot should do in any situation, you can make it a supervised learning problem so that the robot can learn, oh, here in this situation, I have 8 actions. The right action is this one. Let me just do supervised learning. If you have that, that works better than reinforcement learning as well. So you only use reinforcement learning if the environment is so poorly understood that you can't write a control law or even a way to label what action should happen. And so what a reward is, now, of course, in this environment, it's so simple that we can do either of those things if we wanted to. But we want it to be easily understandable in 25 minutes. So, but what a reward is a function from the state to a real value. So the reward of, and sometimes from the state and the action we took. So the reward of being not near a chicken is negative 0.01. The reward of being at your chicken is somewhere between 0 and 1, because it's a dot product of, or I guess negative 1 and 1. It's a dot product of your personalities. And so it's just a number that's associated with a state or a state and action pair. And the beauty of reinforcement learning is that's actually a very sparse signal. You don't know how to tell your robot to accomplish what you want it to accomplish. If you did, you wouldn't use reinforcement learning. Since you don't know how to tell it exactly how to do it, you let it wander around for a long time and let it stumble on the solution, and then let it kind of back propagate the solution back into the space away from the solution so that it can wander towards or follow the gradient towards that solution. Does that kind of answer any questions? So
yeah, thank you so much for that. So the idea here is I have some representation of the world that I'm in. So maybe I'm, near 3 chickens. And I have some actions I can take, which is I can move up, I can move down, I can move left, I can move right. And if I move left, and that's not closer to any chicken that I want to be a friend with, I get this very small sort of negative penalty that says, I'm not doing what I'm supposed to be doing. But then as I get closer and closer to the right chicken, just after moving around randomly, I learned that if I know there's the right chicken nearby and I step in that direction, I get some small positive reward back. And this tells me that I'm on the right path.
that's right. You're still getting penalized as you get closer to the chicken, but you know that the policy in this deep neural network magic knows that, okay, if I keep going this way, I'm going to get that high level reward. And so you have this thing in reinforcement learning called an episode, which is basically, from the start to the end. So here where the robots wander around randomly and they end up at chickens, the episode ends. And what you want to do is you want to maximize the reward over the episode. So you don't always have episodes, but it's convenient when you do. And so, each time step, it gets a little bit of negative, but then hopefully that negative is outweighed by the positive of actually getting to the chicken if it takes a direct path. And a lot of this comes down to your reward engineering, which is one of the reasons why reinforcement learning is so hard or hard to get right. Is let's say that you don't give it, you give it a way to leave the board, right? So let's say that, we just had a robot become conscious and leave the board. I don't know how that happened, but let's say that was one of the things that could happen with a robot. And then you said, okay, you get a reward for getting to the chicken, but if you don't make that reward big enough, the robots will all commit suicide. And that's like a real common thing, that the robots will say, forget it, I'm just going to end the episode as soon as I can and minimize the amount of punishment I have to suffer. And so you have to kind of rejigger the reward. You say, okay, well, I'm punishing it either too much for every time step or not giving it enough reward for getting to the chicken. So therefore, I need to up that reward. Or likewise, it gets a reward for getting to some chicken, but maybe not the optimal chicken based on its personality. So depending on, if it's just going to the closest chicken, but not the optimal one, you may have to say, okay, I need to change that reward a little bit so that it doesn't get as big a reward just going to a random chicken, and it gets more of a larger reward for going to a bigger chicken. I mean, a chicken that's most like it. And so you might say, okay, it's the dot product times 5 or something. And so that's kind of where the all the runs come into play, and you have to do the black arts of messing with the reward function. So that's kind of the downside of reinforcement learning. So it's almost like a last resort. If you don't know much about the problem, you can still get a robot to do something smart if you have a lot of computation.
Awesome, thank you for expanding on that in more detail. There was another question just about about the problem setup. Why robots and chickens?
Oh, yeah, I just wanted the dumbest thing possible. And chickens, for some reason, are just naturally funny to me. Just the idea of a chicken. I mean, I don't know why. And then robots are kind of cute. So robots and chickens. There was no intelligence in it beyond that.
Lots of fun, though.
Yeah, indeed.
Awesome. Looks like we have one more question in the chat here. This is from Jin Xiao, who has just asked, is it a good idea or a general approach to tune reward as a hyperparameter?
Yes. Yes. Yes, and then for listeners, some who may not be familiar, hyperparameter is when you do machine learning, you have a whole bunch of parameters that kind of set up for your problem, like how long the time step is, or how big the change in the gradient of your in your policy. And so there's a whole bunch of parameters, and so you can do what's called a hyperparameter search. And the question is, could reward be one of those hyperparameters? And yes, it could.
Awesome. Thank you so much for that. I think that's the last of the questions, or at least the last ones that I saw here in the chat. If anybody else has any questions, of course, you're free to unmute yourself and ask Jonathan.
Well, cool. Well, thanks everybody for listening. And I look forward to the next talk.
All right, thanks so much, Jonathan. That was great. Awesome talk.